Hey, so I will show you what I have so far for my inductance mirror. So um, first of all, I will try to begin explain the circuitry, like what are my circuit constraints and voltage supply constraints, current constraints, etc., etc. And then I will show you how I built and derive all the circuitry using my product board. So let's begin. So first of all, I found out that you can use this circuit which is called a tank circuit, I think, which if you fed it a high speed pulse or a really low rise time pulse or really low fall time pulse, and it goes through pretty much a DC blocking, or which acts as a high pass circuitry, it will make this capacitance and this inductance ring like it's shown here in blue. And what really happens is that here the pulse is coming through, and I will have a really sharp edge pulse or really short pulse, which is going to charge. It's going to charge the inductance with a magnetic field. Here it's showing blue, because an inductance generates a magnetic field the fastest the change in voltage it goes through, and this will generate a high voltage between the inductance, which it will charge the capacitance. So it will charge the capacitance back to, and then this will go down, so it will discharge its magnetic field, but the capacitance is going to remain charged, and as it says that the inductance is being discharged, it's going to charge it back. It's going to charge it back again, which repeats the process, which goes back and forth, generating the sine wave or the cosine wave, depending on how you solve it. And however, this is not perfect, as some losses are going to happen from heat, from any other imperfections in the components, which is going to dampen it, as shown in red here. And so what I'm measuring here is, in the output, is this red one. So after that, what I do is, this is PO, the same one as over here. I pass it through a DC blocking capacitor, which it's going to remain unnamed, and then it's going through an op-amp to be amplified. I'm going to use a non-inverting configuration, because I find it the easiest to deal with voltage reference, which I'm going to call it later. And I'm using a ratio of R2 to R1, so I can get a gain of 10. So the reason I'm amplifying it's because I'm going to use a comparator over here, and I need that to detect most of the sine wave components over here. So the bigger it is, the more probability I have to detect more, and the more precise the measurement can be made. So the problem is that I'm using the DC voltage supply, so the op-amp cannot go rail to rail if my signal is below its rail. because it's going below 0 voltage and it cannot go below 0 volts. So I'm going to include the Vref, which Vref is pretty much half the voltage supply, and I'm generating it with another op-amp just as a voltage follower with two resistors of almost the same value. And well, the output of this comparator is going to a comparator, and it's going to change when this value goes below and higher than the voltage reference. So if it's below, it will do nothing. If it's over, it will output something like this in green. This is the comparator output, and this digital pulse can be measured in the DINSE more easily, so I can measure this time it takes from going from low to low, and this time is going to use to calculate the frequency of the sine wave. So let me show you the circuitry right now. Okay, so this part in green is this bit over here. This is CT in this circuit. This over here is CV, and this is the test inductance. This is the DC blocking in the capacitor here, which will go on value. These are the resistors for the gain. I'm including a 10 picofarad capacitor here to minimize noise coming from unwanted sources. This op-amp is a TL974. I'm using this for no particular reason. You only need to use a really fast op-amp, at least 4 MHz bandwidth I would recommend. The part over here is the voltage reference supply, and these are the two resistors used to generate the half rate supply, and it's going to the first op-amp and to the comparator. However, the only thing I'm not including here is that I'm including some hysteresis, and I'm not going to go into detail of what hysteresis is, but pretty much it will guarantee that noise doesn't generate extra pulses here, so I'm not measuring something that's not there. So with this circuitry, I can measure the time just as I was measuring the time in the capacitance mirror. So a lot of the circuit changes, the programming software doesn't change, but as I'm going to explain in another video, there are a lot of troubles with this design, which is I'm going to go in a bit further detail in that video, because it has a lot of math which I'm not including here. And so far that's the circuit I'm showing here, and it works really good. So let me but well, I think for now that will be all for this video. In another video I will show you how I found out that my limiting factors are coming from some of the capacitances and values I'm choosing for them, and some of the problems with the code I need to fix to go for it. And in another video I will try to test and show all of the different values here. But for now, that's all.